Ladies and gentlemen, today we are presenting the Fast Fall project, an experimental study carried out as part of our practical physics work, aimed at observing and analyzing the fall of objects under different physical conditions. Although the subject is simple, it is surprisingly difficult in terms of the physical modeling of the experimental data. The aim of this project is to compare the effects of the environment, temperature and height of fall on the movement of a vertically falling object by comparing our experimental measurements with the fundamental laws of mechanics.
One. Fall in the vacuum tube. In this experiment, we observed the fall of an object in the tube with and without air. Even so, we did not remove all the air from the tube while creating a so-called vacuum. We can still notice that the two objects feel almost simultaneously, which confirms the influence of the air resistance during free fall. Fall in glycerol at different temperature. Here the object is dropped into glycerol, a very viscous fluid, at various temperatures. The aim is to study the influence of the temperature on viscosity, and thus on the behavior of the fall. The results are quite revealing. At low temperatures, glycerol is very viscous. The object slows down quickly and reaches a low terminal velocity. At higher temperatures, the viscosity decreases. The terminal velocity increases, and this position curves shows a more sustained acceleration before stabilizing. The curves obtained clearly show that the higher temperature, the lower the viscosity of the fluid. Moreover, we can see that this disgrace is almost linear, but we cannot claim that this observation would still hold if the same experiment we performed on the large scale.
For this part, we carried out a mass drop in order to determine the level of uncertainty for the rest of our approach. After checking the two videos, we noticed that the G is different when the results are extracted. The mass should have a constant G of 9.81, but this is not the case. In fact, according to our results, the G of the mass when it falls from the first stage is 8.5. From the second stage, the G is 6 when the mass falls. From all of this, we can say that our result from the rest of our works will have a large uncertainty, against our will. This can be explained by a number of small errors in the scoring, which when added together create a large uncertainty. In conclusion, even if our results are not very accurate, they can still be used, but they should be taken with a grain of salt. Studying the fall of a steering wheel involves taking into account the drag force, which is highly dependent on its aerodynamic shape. In the case of the steering wheel, the drag coefficient is particularly high, around 1 depending on the model. This is due to its no profile shape, diploid theta, its low mass in relation to its frontal area. The coefficient was estimated experimentally by fitting the curves to a freefall model. To obtain our curves, we dropped two different steering wheels, one made of plastic and the other with the characteristic of a racing wheel. After telling and extracting the data, we realized that the freefall model did not apply to the falls of our two steering wheels, confirming the presence of a frictional force. So we have found a better model. We then determined the friction force and the velocity throughout the fall of our two flywheels in order to plot the friction force as a function of the square of the velocity. We did this because the formula of the drag coefficient is as follows, with F the drag force, ρ the density of the fluid, v the velocity of the object relative to the fluid, and s the reference surface. Finally, we determine the surface area of each by approximating them to a cycle and found the drag coefficient of the plastic wheel is around 0.07, while that a competition wheel is around 1.1. This shows that the racing wheels maximize drag better and therefore slows down more than the plastic wheels when he falls, which is consistent with its sporting use. In a fluid such as air, a falling object reaches a speed limit when the force of drag exactly balances the weight. After plotting the falls of the wheels from the second floor and calculating the speed, we plot the speed as a function of time. Note that the curves become linear when the limit speed is reached. This part is circled in black. The limiting speeds obtained in our two experiments are 5.3 meter per second at 5.2 meter from the ground for the competition flywheel and 7.81 meter per second at 3.67 meter from the ground for the plastic flywheel. We can therefore see that, despite a lower drag coefficient, the plastic flywheel reaches a higher speed limit than the competition flywheel.
Conclusion. This project allowed us to concretely observe how factors such as the presence of air, the viscosity of a fluid, or the shape of an object influence its fall. Despite the apparent simplicity of the phenomenon, the results show that experimental reality can be far more complex than a simple theoretical calculation. The FastFall project thus enabled us not only to gain a better understanding of freefall and resistance phenomena, but also to develop a critical and medical experimental approach to the data collected. It is the scientific rigors that we will remember above all.